So hello everyone, this is Yash Kopulwar and I will be giving presentation on skull fracture detection using maximum intensity projections. So a skull fracture is a break in one or more of the 8 bones that form the cranial portion of the skull. This usually occurs due to severe head injury or head trauma. Skull fractures are often associated with traumatic injury to the brain. The brain can be directly damaged due to the injury to the brain tissues, bruising or bleeding. The indirect effects include blood clot, which can block blood flow to the brain cells or can cause intracranial pressure on the brain. These injuries can lead to life-threatening complications. Therefore, quick and accurate detection of skull fracture is very important. This project aims to develop an MIP-based method to detect and segment the skull fractures by using deep learning models. This is the timeline. So these are the contents of the slides. Firstly, some information about the dataset used. Then we will move on to the pre-processing part, which is a skull segmentation. Then I will talk about MIP, which is maximum intensity projection. After that, the deep learning architecture will be discussed, and finally, some future scope. So the data set was acquired from PhysioNet. This dataset includes uh, CT scan for patients diagnosed with intracranial hemorrhage. Each CT scan includes about 30 slices with 5 mm of slab thickness. The dimensions of the images from axial view is 512 cross 512. Now, to remove the irrelevant regions like clothes, machines, soft tissues, etc., we need to segment out the skull part. This will be done with the 3D CT image. This three-dimensional CT image is made up of cubic voxels, which are equivalent to pixels in the 2D image. The values of those voxels is Hounsfield unit. The Hounsfield unit is the relative quantity measurement of radio density with respect to the attenuation value of distilled water at standard temperature and pressure. Now, as we know the specific HU values for every body organ, we can separate it in the CT image by selecting a specific window of Hounsfield values. This is called windowing or gray level mapping. Windowing will change the appearance of the image to highlight that specific type of structure. Here are two examples of segmentation by thresholding using Hounsfield values. The leftmost images are of the slice of the CT image, of a skull. The middle image shows the voxels with HU values from 300 to 2000, and the rightmost image shows the voxel with the HU value less than 300. So you can see in the middle part the bones are clearly visible, and in the rightmost part the soft tissues are visible. The CT images are three-dimensional. The traumatic brain injuries are checked mostly by analyzing several axial slices of the CT scan. It is not easy to estimate the total damage done to the skull by looking only at the slices, and checking these many slices takes lots of time. The 3D rendering of the CT scan also takes too much time and resources. Therefore, the radiologists use maximum intensity projections to project the 3D CT image, the three-dimensional CT image on a 2D plane. We can see here in this image, to calculate the MIP for each XY coordinate, only the pixel with the highest Hounsfield number along the Z axis is projected onto the final image. This helps to observe the dense structures that are present in the scan. In this project, we are dealing with CT scans of skulls. If we apply MIP on the whole image or the whole CT scan, the intensity of the bones in the jaw and neck will interfere with the final image. The fractures in the skull will not be properly visible because these bones of jaw and neck will be visible behind the fractures. So therefore, to prevent this, we need to look specifically to the calvaria, which is just the top part of the skull. So we will be calculating this maximum intensity projection only for the top part of the skull. So the figure here shows the MIP images with 5 mm of slab thickness without and with windowing. The left one is without thresholding, and the right one is done after applying the thresholding. We can see that the fracture is clearly visible from the starting to end in the right part. Now coming on to the deep learning architecture, we can use the UNet deep learning model for detection in the CT images. It consists of an encoding part and a decoding part. The input to the model will be the MIP images of different slab thicknesses. Here, the encoding part consists of the repeated blocks of two convolutional layers and max pooling. This convolutional layer has 32 component feature map at the starting, and then it doubles after every application. Batch normalization and ReLU layer activation is used after every layer. The decoding part is like reverse of the encoding part. It consists of upsampling layers followed by concatenation with the corresponding feature map from the encoding period. This decoding part has 128 component feature map in the starting and it halves after each block. Now, for the future work, the data used here was downsampled by a large extent. In high resolution images, we can alter the slab parameters to get required MIPs. We can use 4 connected neighborhood operator to separate the unrelated tissue from the bone tissue. This 4 connected neighborhood operator can also be applied in 3-dimensional instead of applying only on 2D slices. This will be beneficial for higher resolution of 3-dimensional CT images. And also instead of simple MIP, different techniques can be used like curved slab MIP, rectangular MIP or weighted MIPs. The detection method can also be compared to the segmentation method. That's all for the presentation. Thank you.